The next set of notes continues to look at ways that we can incorporate explanatory variables in our model. In this particular section of notes, we look at ways that we can do polynomial transformations of our explanatory variables to help represent nonlinear relationships between the explanatory variable and the logit of pi. Our focus will be on quadratic terms, meaning let's say we have an x squared in the model in addition to just having x alone. Now you may think that the way that we would include a polynomial transformation, or again quadratic term in our model in the formula argument of GLM is to do something like this, where we have our response variable y, we separate it from the explanatory variables by tilde, and then we say x1, the first explanatory variable, plus x1 caret sign 2. Unfortunately, this does not work. Here's why. In the last subsection of the notes, we looked at interaction terms where we had, let's say, x1 plus x2 caret sign 2. And what that represented was a model that had x1 in it, x2 in it, and x1 colon x2, in other words, the interaction. That's what the caret sign represents in the formula argument. It does not mean square it. And so because of that, we have to use a slightly different set of code. And what we can do is with this x1 caret sign 2 is enclose it with inside the I function, which basically means identity function. And simply what this function does in R, it tells R to say, hey, treat this as you would normally, not necessarily how you would treat it in the formula argument itself. So that treat it as actually a quadratic, a squared term in our model. So the correct way then to write out a particular model, I should have started off with this to begin with, sorry. The logit of pi is equal to beta 0 plus beta 1 times x1 plus beta 2 times x1 squared. The correct way to write out that model then is to have the I function inside your formula argument, where inside of it you have x1 caret sign 2. So given that then, well, how would you code then this particular model where we have quadratic terms, we have an interaction term? What could you do? Well, it's not too difficult. You could say formula equal x1 plus x2 plus x1 caret sign, plus x1 colon x2 to get the quadratic term. I guess I should have waited till the end to do that one. Then plus the identity function of x1 caret sign 2 plus, again, the identity function of x2 caret sign 2. That's how you could code that particular model. Now, what happens then to odds ratios that we use to interpret the effect that the explanatory variable has on the response when you have a quadratic term in the model? So again, suppose we have this simple model with the main effect, you could say, x1, and the quadratic term, x1 squared. What happens to the odds ratio for x1? Again, go back to basic principles about what an odds ratio represents. It's a ratio of two odds. The numerator odds corresponds to the odds of success when you have x1 plus c, the denominator where you just have x1 itself. And so wherever we see an x1 in that numerator, we replace it with x1 plus c. We do a little bit of algebra, and this is what we get in the end. The exponential function evaluated at c times beta 1 plus c times beta 2 times the quantity 2 times x1 plus c. Now, this is the first time that we've seen an odds ratio for a logistic regression model where the explanatory variable that we're trying to interpret, that explanatory variable is in the odds ratio itself. This then causes some problems then in interpreting this odds ratio. So here would be then the standard interpretation. The odds of a success are, whatever the odds ratio is, times as large for x1 at a particular numerical quantity than for x1 and another numerical quantity. So for example, let's say I want to do an odds ratio for distance in the place kicking example, where I have distance and distance square in the model. I would need to do this kind of interpretation for, let's say, a distance of 20 to 30 yards. Also, I would need to do it for 25 to 35 yards. I would need to do it for 50 to 60 yards. I always need to specify then what specific distances I'm talking about, because x1 is in the odds ratio. X1 has an effect about what that odds ratio is. So because of that then, whenever you have a quadratic term in your model, you're going to probably need to calculate multiple different odds ratios to fully interpret it. So how can we do inference then for these odds ratios? Well, we can do a walled confidence interval. We can do a profile likelihood ratio interval. Profile likelihood ratio interval proceeds in much the same manner as before. We have the MC profile package, which helps do those calculations. For a walled interval, here's then the corresponding expression. We take the estimate of this part of our odds ratio, so the corresponding estimate of that, plus or minus the value from the 1 minus alpha divided by 2 quantile from the standard normal, times then the square root of that estimated variance. Where does this estimated variance come from? Well, here's how you would calculate it using methods that we've seen before. You find the individual variances and covariances from the estimated covariance matrix. Once I have the confidence interval for just, again, this part of my expression, then I can use the XP function with it to find the walled confidence interval for the odds ratio. Okay, so let's take a look at an example here. Let's say I want to go back to my place kicking example. Note that the corresponding R program is separate from placekick.r. The reason being is because this example is actually an exercise in my book. And so here's a separate program that I use to do parts of the exercise. In this particular place kicking example, I want to use distance to estimate the probability of success, where I'm going to let x be my distance, and I'm going to include a quadratic term in the model with that x. Now, how can I estimate that model? Well, I'm going to put the results into mod.fit.dist square, or SQ, use a GLM function, specify my response, good. Then I have distance plus distance squared, where I use the I function around the distance caret sign 2. Excuse me. I can summarize then the model's fit, and here's the corresponding results. Here are my beta hats. Notice how R labels that distance squared term in this table. So with that, then I can state my estimated logistic regression model as the logit of pi hat is equal to beta hat 0 plus beta hat 1 times the distance plus beta hat 2 times the distance squared. So here's the 0.0017536, and here it is right there as well. We can perform a walled test as what we've done in the past to test, is that quadratic term important or not? In other words, is beta 2 equal to 0 or not? And I can come back up to my table once again. I see the corresponding p-value is 0.027. So there is marginal evidence that indeed this quadratic term is actually important. I could also do a likelihood ratio test as well, where let's say I estimate my model as I've done before with just distance in the model. So this corresponds to my HO model. Then I can use the ANOVA function also as what we've done before, where I put the HO model first, the HA model, which allows for that distance interaction, put that second, say test equal chi-SQ, because I want a likelihood ratio test. And here is then my -2 log lambda statistic. Here's the corresponding p-value. So again, marginal evidence that indeed a quadratic term is important for this particular model. Let's do a plot of the model. The corresponding code is in my program. So the red line represents the model with just distance in the model. So you can say just the linear term. The blue line is the model with both distance and distance squared in my model. And you can see largely for most distances, the models are very, very similar. Really, the difference starts occurring for these longer place kicks. Now, unfortunately, though, we don't have much information about these longer place kicks. So notice, for example, we have just 3 observations there, based upon what we've seen before. I know that these are just 0 successes out of 1 trial. Up here, we have 1 success out of 1 trial. So for a distance of basically 55 yards and higher, we only have 5 observations. And this is where the biggest difference exists. And so really from what we have with this model, it's really difficult to make a judgment of, is there truly a quadratic effect that's needed with this corresponding model? Later in this course, later in my book, we will actually take a closer look at this through other mechanisms to determine, indeed, do I need a distance squared in my model? Okay. Now, on your own, please see my corresponding program about how to do the confidence intervals for the odds ratios. Use EM means, use MC profile. It follows from what we've seen in the past. For those of you who are in my course, if you have any questions, please feel free to ask during our class. And the last thing I want to mention is that there are other ways to represent a nonlinear relationship between an explanatory variable and the logit of pi for a logistic regression model. In particular, in the later chapter of my book, I talk about the use of splines. Splines are a very flexible way to represent nonlinear relationships. For those of you who are taking my course, sometimes I will talk about using splines, while other times I will not. Just depends upon the semester and the focus of like some of the projects that we have during the semester. Now, also I want to mention is that the splines topic in my book is only in the 2nd edition and above. So please take note of that. Okay, so this is a really quick introduction to the use of quadratic terms in a logistic regression model to represent nonlinear relationships between the logit of pi and the explanatory variable.